My name is Elette Boyle. I'm a senior scientist in the CIS lab at NTT Research. The work that I do focuses in some area that's called secure multi-party computation. We have tremendous solutions for protecting data while you're sending it or while you're storing it. But we're still really working on solutions for how can you protect information when you're actually wanting to use it. And this is where secure computation comes in. For example, suppose that you're buying something online. You need to send your credit card information. You need to verify, is this website really the website that they claim to be? On the other side, they get this encrypted information, but in order to actually do anything with it, they have to decrypt it. I'm not so happy that they have my credit card information. I have to trust they're not going to do something else with it. And on the flip side, it's their burden to protect my private credit card information. Is there some way that I can make this transaction that somehow, for example, we could run a protocol and the transaction could go through without ever needing to reveal that information directly? So there's ways of doing this. And one of them, you take your information and you kind of break it into pieces. This approach takes these pieces and starts performing computations on the pieces with a little bit of talking back and forth. The second approach sort of takes that computation and scrambles it, or sort of, encrypts the computation in some sense. And then I can give you this scrambled program and you'll be able to compute it on input. So a third approach to secure computation is called fully homomorphic encryption. This is a form of encryption where I can take my secret information and encrypt it, send it to you. You don't know anything about what's encrypted, but even without that knowledge, you can somehow perform computations on the encrypted data, okay? Such that now whatever you've computed, you send that back to me, and I can decrypt and learn some function applied to my original secret. So an even more recent approach to secure computation is something that I've been a part of, which in some sense has observed that fully homomorphic encryption is a little bit of an overkill for this task. And it turns out that you can relax, you can consider a weaker object, which still suffices to give you these secure computation protocols. And this is something, notion that I put forth with a couple collaborators that we call homomorphic secret sharing. And in fact, we've already been able to show results where you can build this with lighter weight cryptographic machinery, less kind of heavy math, with different sorts of structures. Part of my research goal is to try to take these secure computation solutions and bring them to a point where they can become practical, that we will get back to a phase like the original introduction of the internet, where things were safe and you could kind of trust everything. Now you can't do that directly, but hopefully we'll be able to build tools that can allow that.
We're not here to just change the world. We're here to upgrade reality.